So whenever you want me to, go ahead.
Okay, so the next speaker is Theresa Anderson from Purdue University, and she'll talk to us about adhesion dyadic systems. Is this?
Okay, pues muchas gracias por la invitación de hablar aquí hoy, aunque no estamos en la Argentina. So thanks to the organizers for inviting me today. I wish I was in Argentina, but this is the next best thing. So let me go ahead and flip to the document camera. And there's the title of today's talk on adjacent dyadic systems. And you might also hear me refer to them as distinct dyadic systems. And as I'm giving a Blackboard talk on paper, if you're having trouble seeing or hearing me, please just unmute and let me know. Similarly, if you have questions during the talk, probably the best way is just to simply unmute and ask them. So questions are definitely welcome. All right, so before I talk about what adjacent dyadic systems are, let's just remind ourselves about dyadic grids and why they are important and what basic properties they have. So as I'm speaking to a bunch of analysts, we know that dyadic grids and dyadic decompositions are very important and well used in harmonic analysis. And the key properties of a dyadic grid and Euclidean space include something like the following. So first of all, the union of cubes at a given level. So where the cubes are, say, the side length is 2 to the k. This fills up the whole space for k a given level. That is an integer. Another key property is that you have this nice intersection between cubes. If you intersect two cubes, you either get one, the other, or the empty set. And finally, we have a nice parent-child relationship. So this isn't everything, but this pretty much sums up the desired properties that we like to see in dyadic grids. So each cube has one parent and only one, and each parent divides itself into two children of equal size. And as an example of a dyadic grid is, of course, the standard grid that we use frequently. So the standard grid on the real line consists of intervals of length 1, half open intervals, so 0 to 1, 1 to 2, etc. And then we would have 0 to 1/2, 1/2 to 1, etc. and so on. And then we would also have the larger cubes. A key point to note here is that 0 is essentially a branch point. So there's always going to be cubes emanating forth from 0. 0 will never be an interior point in any cube. That's a key feature of the standard grid. And that is due to the choice of how we choose the parents. The next example breaks this feature. And this is sometimes called the shifted 1/3 grid. So 1/3 shifted grid. And I'll abbreviate this as D 1/3 or G 1/3. And this is best seen by drawing what it looks like. So we'll have the point 0, we'll have this point 1/3, 4/3, and 7/3, and so on. And then minus 2/3 and minus 5/3. So first we take the standard grid, which starts at 0, and we shift it to start at 1/3. So the cubes of side length 1 would look like the cube 1/3 to 4/3, 4/3 to 7/3, and so on. For the small cubes, what we do is just do the usual parent-child relationship. So when you want to find the children of this cube, just simply divide it in half and so on. And that will completely and uniquely determine all the smaller cubes. For the larger cubes, we're going to do something different, and we're going to alternate the choice of parent. And we can enumerate this by 0s and 1s. So alternate parent choice, and we will use 0 for the right child.
Tess, can you move the page up a little bit? It's out of frame. Thank you.
And 1 for the left child. And what this looks like is for this cube here, our starting initial cube, we're going to choose firstly the choice of parent where this cube will be the left child. So the parent will be 1/3 to 7/3. But then instead of choosing the grandparent to be 1/3 and going forth this way, we're going to choose it the other way. So we're going to choose the grandparent cube here of -5/3 to 7/3. So first, the parent was such that this was the left child, and the grandparent was such that this was the right child. And now when we choose the next generation, this will be the left child again. And so we're going to be alternating what child we are by parent choice. And so first we did the left child and then the right child. So left child is a 1, right child is a 0. And so our choice of parents is represented by this infinite sequence here of 1s and 0s. And we're going to use this initial cube to choose the parents, and this will uniquely determine the grid because we can fill out all the other cubes such that the whole space is covered. And what this does is this allows that point 1/3 to never become stuck, like 0 becomes stuck. So if we go up just 2 generations, we can see that 1/3 is now an interior point of our cube. Whereas with the standard grid, 0 will never be that interior point. So this is a very useful property. And indeed, when you combine these 2 grids, you get something very special. So D and D 1/3 are an adjacent dyadic system. And what that means is that you have this feature of never having these points becoming stuck and never being interior. And more precisely, this feature is that any interval is contained in a dyadic interval of roughly the same size. So when you combine these 2 grids, any interval at all, it doesn't have to be dyadic, any interval at all is going to be contained in a dyadic one from either D or D 1/3 of roughly the same size. And moreover, to be an adjacent dyadic system, the number of grids will be minimal such that you have this property. So this property is sometimes termed as May's lemma. And May's lemma, you can quantify this. And I'll write one such version for the real line. This is named after Tao May, who did this for the torus. And the precise version is for any interval in R, there exists a Q in one of the 2 grids. So generically, we don't necessarily need D and D 1/3. We just need 2 grids, D1 and D2, such that I is contained in Q. So the interval is contained in Q, and Q has roughly the same size as I. So this is the length of Q is bounded above by some constant that only depends on the dimension times the length of I. So I and Q have roughly the same size. So you can have various versions of May's lemma depending on how good a choice of constant you want. And this lemma, even in itself, has a rich history, which I won't go into here. But this property is very useful, and this is the key defining property for an adjacent dyadic system. All right, let's talk about a few brief applications to having an adjacent dyadic system. And then we'll talk about how to classify all of this.
I have a small question before.
Sure.
So small cubes you are taking for D, is that right?
The small cubes are just determined by dividing each cube into half.
And you're taking both for both grids, you're taking small cubes for both D and D1/3. Is that right?
Yes. Yeah.
Okay. Okay.
So the key difference here is really this parent structure with the alternating choice of parents. That will become a little more relevant later on in the talk, how that parent choice is different when we talk about classifying these systems. All right. So for a quick application, we have an application to the Hardy-Littlewood maximal function. And that is that the dyadic version is a lower bound for the usual continuous Hardy-Littlewood maximal function, but it has an upper bound of a sum of the dyadic Hardy-Littlewood and the 1/3 shifted dyadic Hardy-Littlewood. So this is, if you just want to think of it on the real line, the usual continuous Hardy-Littlewood maximal function. So it takes a nice enough function and replaces it by its average, the soup of the average of the function at every point. So a nice smoothing operator. The soup of all the averages are taken over every interval, no matter what size. This can be sometimes difficult to study. So instead, what we can do is we can only restrict the intervals that we're souping over to dyadic ones. Because it's bounded below by MD, the restriction to the dyadic intervals, and bounded above by a finite sum, only 2 elements of MD and MD1/3. And so in practice, sometimes it's much easier to study the Hardy-Littlewood maximal function via studying its dyadic version. And because we have this nice bound on each side, we can reduce many problems to studying the dyadic version. The second application, and I won't go into details on this, is the area of sparse domination. And again, this uses a very similar variant to this principle to bound operators above and below by certain dyadic versions. And this type of technique, sparse domination technique, has been used in a wide variety of settings. It's a very active area in harmonic analysis. For instance, this was used to solve the A2 conjecture by Andre Lerner using this technique after Huttonen's original proof. And as I said, since has become very active. So these are 2 areas of applications. And for some history on adjacent dyadic systems, May's lemma, a lot of these applications, and the term, which is sometimes used, the 1/3 trick. So a more extended variant of the 1/3 trick involved adjacent dyadic systems, but as originally stated, using D and D1/3, you might see this under the title, the 1/3 trick. I refer you to the excellent monograph of David Cruz Uribe, who tracks down a lot of primary sources and gives a nice history of this, and you can find this on the archive. So I unfortunately won't have time to list all the history here, but this area has quite a rich history. So I'm going to jump ahead to the question on the real line of classifying all of these systems. So I just told you that the standard grid D and the 1/3 shifted grid form an adjacent dyadic system, and adjacent dyadic systems have these nice properties that have all these nice applications. So a natural question is to try to classify all of them. So the standard grid and the 1/3 grid are great and they work, but are there others? And one work in this direction was by Lee, Pfeiffer, and Ward. And what they did is they showed that you can replace 1/3 by delta, where delta is a far number, which I will define shortly, and you'll still get an adjacent dyadic system. Okay, So now this gives us a lot of different ones. I'll show you the definition of far. And if you think about it a bit, you'll realize there are a lot of different far numbers. And so hence a lot of different adjacent dyadic systems. But then you might ask, is that all of them? And the answer is no. And the next question is, what are all of them? Can we classify them? The answer to that is yes. And that was done in work of myself, Bingyang Hu, who is now a postdoc at Purdue, and then 3 undergraduate students, Zhang, Olson, and Wei. And this was in a summer program I ran at UW-Madison. This paper is in Math Annalen and it appeared last year. We classify all adjacent dyadic systems on the real line, and I'll discuss some of the details in a moment. And then there's a follow-up work, which I'll mention at the end of my talk, of myself and Bingyang Hu. And this is on the archive in preprint form. And in this paper, we classify all adjacent dyadic systems in RD. So I promised a definition, first of all, of these far numbers, so you can see more examples of adjacent dyadic systems. And this is where the number theory comes into play, because this is a very number theoretic condition. And I'm going to extend this definition to n-adic grids, but if you would like, just think of n being 2 for the purposes of this talk. So delta in R is n far, if and only if the distance from delta to rational point of the form k over n to the m is bounded below by a constant that only depends on delta over the size, the scaling size, n to the m. This is for all m greater than or equal to 0 and all k and z. So if you think about this, first of all, this looks highly number theoretic here. If you multiply your numerator by n to the m, so if you multiply through by n to the m, you'll see this looks like a very number theoretic condition. And indeed, you can use a lot of number theory to generate these n-far numbers. So this is something I did in my PhD thesis. And if you relate this to grids, you'll see that this is the endpoint of the standard n-adic grid. Again, just think of n being 2. These are what the endpoints look like, at least for the small cubes. And what this condition of being far says that delta repels the endpoints of your grid by an absolute constant over the scale. So for every scale, no matter how small you go, delta will always be c delta away from those endpoints. So this indicates that this point delta is somehow apart enough from every single cube of your standard grid, no matter how far down you go. And the fact is that delta equals 1/3 is too far, and I've alluded to that already. And as I said, you can use number theory to generate a lot of these, but I will give a fact that was included in the Math Annalen paper, that delta is n far if and only if the sup of the length of ties is finite. And a tie is, if you take delta and you expand it out in binary, or more generally an n-ary, but let me just list the binary expansion for now. If you have a delta that looks something like this, etc., this is a tie of length 5. So if the sup of the length of ties is finite, you have a far number. And so this provides an easy classification to generate these numbers, and therefore to generate a lot of these adjacent dyadic systems.
Tess, can I ask you something?
Sure.
So this is for the, so this will be, so the binary will be for the two far numbers, right? So if you had n far, then you will use 0 up to n-1, and you'll have
yes.
Okay, great, thank you.
So for n-ary, yes, you're expansions will include zeros through n minus ones.
Mhm.
The ties will only refer to the zeros or the n minus ones. So it's a little hidden in the binary, but if you have a ternary expansion, you'll only be worried about the zeros and the twos.
Okay, thank you.
All right, so this is what the FAR number looks like. And to list our results, this one up here, we need another concept as well. So as I said, the 2FAR was in the paper by Lee, Pfeiffer, and Ward, but we're going to introduce another concept before we can classify all our grids, and that is the location function. So the location function will apply to the large cubes. As you can imagine by the fractions appearing in the FAR numbers, these are really going to be relevant for the small cubes. The location function will be relevant for defining the large cubes that we can have. We're going to take a sequence A of A0, A1, A2, etc. Then the location function is defined by LA of J is the sum from L equals 0 to J minus 1. A sub L, n to the L. So again, I'm doing this for n-adic grids. Feel free to just think of n as 2. And then also we need to define that LA of 0 is equal to 0. This gives the location of the initial point. So for the standard grid, this would be the initial point 0. For the 1/3 shifted grid, again, I would have to specify the sequences, of course, but this will give the location of the initial point 1/3 after choosing J ancestors. So this tells you exactly where your initial point goes to when you choose J ancestor generations. So for that 1/3 example, our location function involved the sequence 1, 0, 1, 0, and you plug it into here, and this will tell you exactly where that initial point 1/3 will go to after J ancestor generations. And a fact is that you can write any grid, once you define this location function, as G of some initial point delta. This might not be FAR. So just any initial point delta and a location function LA. So this is our initial point, and this is our location function. This representation might not be unique. Indeed, there are many, many different representations we could choose either by varying our delta or varying our location function. But shortly we'll see that it doesn't really matter that a representation is not unique. We'll be able to have a uniformness to the theorems that I'm about to list. And so the first theorem involves classifying all of these. And it says, so this is in the math Anolin paper. It says, let G1 be some G with initial point delta and location function LA1. And G2 be some G with initial point delta 2 and location function LA2. These are adjacent, so they form an adjacent dyadic system. If and only if the difference between the deltas in absolute value is n FAR. And 2, that 0 bounds the lim nth of the normalized difference of location functions. So we're going to take the two location functions at scale J, normalize them with the size of the scale. So this n to the J is the size of the cubes at ancestor generation J. And the lim nth of all these differences will of course be bounded above by the lim sup of all these differences. And this will be bounded above by 1. The key feature here is that the lim nth stays away from 0 and the lim sup stays away from 0. That is, we never get an extremal location. And an extremal location will correspond to cubes at the large scale lining up. And we don't want these cubes to line up because we want to maintain this apartness, this spread outness at the large scales to avoid the problem that the standard grid has, and that 0 point will never be interior. And so this condition is what captures that you never get these location functions being extremal, meaning that their normalized differences never hit 0 and never hit 1. Okay, so these two conditions precisely determine if you have an adjacent dyadic system. The example that we've been running around with is d1/3. And we already said that 1/3 is too far. That's the difference between delta 1 and delta 2. Our delta 1 is 0, or delta 2 is 1/3. So 1/3 is too far. That can be checked easily using some number theory, or you can do the expansion trick as well. And we also can calculate precisely LA1J minus LA2J for these grids. And this isn't too hard. You can even do this during the talk if you'd like. This is either 2 to the j over 3 or 2 to the j plus 1 over 3. And so in either case, if you normalize this by 2 to the j, you either get 1/3 or 2/3. And 1/3 and 2/3 will always be away from 0 and 1. So this will satisfy condition 2. And the proof I won't go into, but it uses contradiction.
So Tess, can I ask you something? So again,
Sure.
you're in the R case and the dyadic and the truly dyadic thing. So really, is the theorem for too far again here, like in the example?
So this extends to n far and n adic. So this example is too far, too adic. So this is the adic case.
And even two grids. I'm just thinking like
two grids, yeah.
Okay.
2 grids. So 2 grids is the optimal number for adjacency. So adjacency is not only the minimum property, but that you also have the optimal number, so that if you take away one of the grids, you won't have this property anymore. And so the optimal number on the real line is 2. So this is all supposing that you're working with 2 grids here.
Thank you.
So yeah, it's kind of cute and maybe a little confusing. The 2 is for dyadic, but we're also working with 2 grids. So that's a good point to keep that straight. All right. And I mentioned before, the representation isn't necessarily unique, but we do have a uniformness of representation. So you can write a grid as G delta LA. It might not be unique, but that doesn't really matter. So this theorem also appears in the same paper. And it says that if we have 2 representations of G1 and G2, so you have 2 grids and 2 representations each, then that lim inf and that lim sup that appeared in the previous theorem are either the same or they're inverted. So there's only 2 possibilities for the lim inf and lim sup. So you either get constant C1 and C2, or choosing different representations, you get constants 1 minus C2 and 1 minus C1. These are the only options. So for the running example, our lim inf was 1/3 and our lim sup was 2/3, the difference between the location functions properly normalized. For any other representation you choose for those grids, you'll either get 1/3, 2/3, or 1 minus 1/3. 1 minus 2/3, which is 1/3, and 1 minus 1/3, which is 2/3. So you actually always get 1/3 and 2/3 for that example. But in generality, these are the only possibilities. So you have a uniformness theorem as well. In the last few minutes, I wanted to mention the results in RD and also the different base case RD, the difficulty stems from the fact that D+1 is the optimal number of grids for adjacency. So in the real line it is 2, which is very nice. And you might think it might be 2 to the D once you go up in dimension, but it's not, it's D+1. And this was shown by Jose Conde, this optimal number. And so this makes the analysis a lot more difficult. Indeed, this paper is a lot longer, the one with myself and Bingyang Hu. And one of the intricacies is due to the geometry and how to analyze certain situations of intersections of cubes. And so I'm going to just mention one of the subtleties here. And the subtlety occurs when you look at boundaries of two cubes that intersect. On the real line, cubes look like intervals. And so if you look at intersections of boundaries, you either get a single point or you get the empty set. For R2, so even just going up once in dimension, you can have intersections that look like this. And in this case, the cubes again intersect in points. So you have intersection of the boundary here and 2 points. And if you project these points down to the x-axis and also to the y-axis here, you have a separation on both of these axes. This is a really nice situation. However, you can also have this situation where you're looking at two cubes whose boundaries intersect on a variety. And this one-dimensional variety here, which is our intersection of the boundaries, when you project it down here, is just a single point. When you project it over to the y-axis here, you have the separation, but you lose the separation when you project to the x-axis. So this situation turns out to be very bad. So this subtlety, which doesn't appear in the real line case, complicates things in the d-dimensional case. But we are able to prove a very similar theorem in the end. And via a lot of pictures in this paper, you'll be able to visualize that as well with running example. I won't go into that example in this talk, but if you like to look at pictures, feel free to take a peek at that paper. And we do have a corollary which has a simple form of a statement to write down that I find very satisfying because it does, in the end, reflect the case on the real line. So this is the d-dimensional case. G1 to G D+1 grids are distinct if and only if the projection of any two of them onto every coordinate axis, so the projection onto every coordinate axis, are distinct in R. So in the above picture here, projections like this are great because they maintain separation. Projections like this are not good because they do not maintain separation. So you still can compare the d-dimensional case at the end of all things to the real line case, which is quite satisfying. And finally, just to mention the different base case, this is in another paper of myself and Bingyang Hu, a different paper. And it stems from asking the question, what if you have a dyadic grid and a 5-adic grid, for example? So one of the types of questions you can ask is the standard dyadic grid and any 5-adic grid. So this is, instead of dividing into 2 children, you would divide into 5 children. So you can take the standard grid and any 5-adic grid, any shifts, any location functions you want. And the question is, will they ever be adjacent on, say, the real line? And the answer to this question is no. And the result is that the bases have to be powers of the same thing. So in this separate paper of myself and Bingyang Hu, for any 2 grids, so again, we have a result for RD in that paper too, but I'll just list the result for the real line. To be adjacent, the bases must be powers of n. So they must be powers of the same number n. So you can never have a 2-adic grid, such as the standard grid, being adjacent from any 5-adic grid whatsoever, no matter how much you shift the initial point, and no matter what choice of location function you choose. And that completes the study of these types of adjacent dyadic systems and classifications. This one relies on a lot more number theory and some elementary number theoretic facts. And I think I will stop there and thank everyone for listening.
Thanks, Theresa. Any questions or comments? I see that a lot of questions are made during the talk, so I don't know.
Oh yeah, absolutely.
So may I ask something
Christina.
for the last theorem that you presented? So you're saying so the theorem forbids so if you have 2 and 6, for example, with things that are so that's forbidden too.
That's forbidden. Yeah,
Okay,
yeah,
great,
that surprised
awesome.
me a little bit. I was thinking at first that maybe things that weren't co-prime would be okay, but 2 and 6 are forbidden.
Okay.
So yeah, you need 2, 4, 8, just powers of 2.
Beautiful talk, and it's actually, I mean, it goes at a gentler pace when you write.
When I write it out.
Yeah.
Yeah, that's the goal. I can't get too ahead of myself. Only limited by my writing speed.
Okay, any other questions or comments?
I have a quick question, but I don't know.
Yes.
So you said that this I don't remember how you call it, this n far points. You rely on some number theory, and I was just thinking it's kind of the opposite of not exactly the opposite, but to this Diophantine approximation. Well approximated numbers in number theory, and
oh yeah, it definitely has that flavor with the inequality in the other direction.
Right, and so you can sort of estimate the dimension of this well approximated number. So I was wondering how, if using that you could say, okay, like there is as much as n far numbers, like you estimate the dimension of n far numbers or such, and that would limit somehow.
Yeah, so we have some facts about related to the dimension in the Mathanolan paper. So if I remember correctly, they're dense, but they have measure 0 and they form a meager set on the real line. So we have a few facts, but there's likely many things we didn't cover about the dimension. They're related, but different from normal numbers. So some of those techniques might apply. Yeah, there's a lot of interesting questions that one could ask about the dimension of these numbers and how they relate to other numbers that frequently arise in number theory, like normal numbers or well approximated numbers, if there's any relationship. As far as I know, there's no real containment with of the set of far numbers in any of the other sets I've worked with, but perhaps there's a set of numbers that is used in number theory I'm not aware of that contains these numbers. And I think there are definitely some things to explore here, as this is a highly number theoretic property and it's probably used frequently in circumstances that I'm not aware of.
Okay, so let us thank Theresa again. And okay.